We are continuing our program with invited plenary speech of a very distinguished researcher with whom I had the honor to work with as a part of ESAC on the Decarbonization of Buildings report. Brian Norton's research has made significant contributions to the development of solar energy technologies and wider aspects of building energy efficiency and sustainability. Sole author of 2 books and co-author of another 9 books, over 500 research papers, including 200 in major international learned journals with over 14,000 citations, H-index of 60, supervised over 55 PhD students. He serves as Associate Editor of Solar Energy, the premier international journal in the field, and serves on 8 other editorial boards and been awarded over 15 million euros in research grants. He's a member of Royal Irish Academy and a fellow of Irish Academy of Engineering. He has honorary doctorate in University of Technology, Troyes, France. He has received Napier Shaw Medal. He is a member of Chartered Institute of Building Service Engineers. He has received the Roscoe Award from Energy Institute. He's a honorary fellow of Chartered Institute of Building Services Engineers with their highest honor. He is a co-author of 2012 American Association of Publishers Prose Award-winning book, Comprehensive Renewable Energy. He is honorary professor at the University of Ulster, Harbin Institute of Technology, and Beijing Wuxi University, both in China. Adjunct professor in University of Houston. I think his CV is really impressive. And he is going to give us today a lecture on strategy of decarbonization of buildings. Brian, the floor is yours, 45 minutes.
Good morning, ladies and gentlemen, and thank you, Nevin, for that introduction, after which anything I can say will only be disappointing. What I'm going to talk about is decarbonisation of buildings, and let me do the health warnings at the beginning. There is no single strategy for the decarbonisation of buildings. It depends on the climatic context, the function of building, occupancy, and many, many other economic, social, and cultural factors. And I advise any of you working in this field, when you look at any advice in this area, whether it's in a textbook, online, or wherever, to look where the persons are located, what tacit, what unwritten assumptions have been making about the built environment as they devise their strategies. The other thing I would say, by way of sort of a health warning at the beginning, is that buildings are not primarily energy systems. They serve another primary function. So, for example, this room is a lecture theatre. Its primary function is to serve that role, and it needs to do it energy efficiently with the lowest carbon emissions. But if you do that and it doesn't serve its primary function, it's failed at its point. And I'll be making that point a few times within this talk. So you can't just look at buildings as energy systems. You need to always be cognizant of the primary function. And just before I start, just like the work presented here comes out of work that I had the honour of co-chairing in the European Academy's Science Advisory Committee, and also work that's funded by research funders in Ireland, where I'm based, and by funders of Velux notably in Switzerland, NSF in the US, and the EPSRC in the UK. So get my thanks to the funders in early. Okay, some of what I'm going to discuss, certainly the early part of this talk, has already been touched on by others and would be well known to people in this room. So in the later part of the talk, I'll talk about some of the more quirky aspects of decarbonisation of buildings that may be less well known. Okay, well, the first thing is, why are buildings important? If you're trying to look at the EU perspective, looking at emissions and climate goals, buildings consume about 40% of energy use, large amounts of gas overall. That varies with context. So where countries have, for example, high renewable energy contributions anyway, perhaps from hydropower, as you might see in some countries. Obviously, renewables contribute more. In other countries, coal, notably. Where I'm from in Ireland, there'll be a very strong penetration of oil into the housing sector. But broadly speaking, there's a huge opportunity for reduction. That reduction can be readily met by electrification and by particularly the adoption of heat pumps and district heating. So there's wide opportunities to seriously address the emissions from buildings. Essentially, what it's trying to do is reduce the emissions from the building itself, decarbonise the building. That is by introducing measures that are going to reduce the heat loss, perhaps increase the solar gain, store some of the heat and electricity that's generated perhaps by solar panels, solar thermal, photovoltaic systems on the building, so that the building is able to reduce the amount of energy it consumes and export energy into district heating networks or to the grid. So you're decarbonising at the demand side in the building itself. That also, by the way, requires a market that enables that demand side energy sales to be enacted. So your building occupants move from being consumers of energy to also producers of energy, so-called prosumers. And that's another sort of side of it in terms of whether that market actually exists so that those transactions can take place. The other thing that needs to happen is that the residual electricity to meet those heat pumps, for example, that comes to the building, is met from decarbonised sources, is met from renewable energy primarily, although if you regard nuclear as a decarbonised sustainable source, it could be met from nuclear. And that needs to increase substantially, and actually needs to increase substantially over the amount of electricity in total that's currently generated. Because you're also seeking to decarbonise industry, you're seeking to decarbonise transport, so electric vehicles. So there's a lot of other demands on decarbonised electricity. One thing, and I'll come to it a number of times in this talk, is that balance between to what extent you decarbonise the supply and to what extent you reduce the energy requirement of the building itself. And if you did it at a technical level, that would be a kind of marginal abatement cost curve. You look at the optimum between whether the investment at the demand side was appropriate or investment at the supply side. The challenge with that is that the boundary conditions for those calculations are continually changing, and new technologies are emerging, for example, and there are various externalities, hidden assumptions in there, for example, that people are rational economic actors, that make those kind of things problematic. Also, there are instances where, as we'll see later, where people do not have the ability to pay for the measures that they rationally should take, so-called fuel poverty, and that comes into equations as well. So there's intersections between energy policy, social policy, as well as, if you like, the division between supply and demand side. Also, there tend to be, in many systems, entrenched actors who want to maintain their market positions, so that you discussed earlier on, for example, the people who maybe want to bring hydrogen into a domestic building situation. In my view, a completely mad idea. But the idea is because the gas industry saw the electricity industry became vectors for renewables and saw an opportunity for themselves to occupy a similar market position. So incumbent actors also influence the reality of how these things get played out. So essentially, you'll reduce the energy demand, and you can see a little graph on my insert there of how actually building regulations for new buildings have gone down over the years and have tighter and tighter requirements, and supply decarbonised electricity, decarbonised heat from district heating to those buildings as the combined strategy that needs to be adopted. And this is part of a long journey, and I'm grateful for this particular paper this year, a paper by Torelli and Bassano, which kind of summarised, if you like, the trajectory of how things are going to change in buildings, and also some of the nomenclature, from business as usual to near energy buildings, near zero energy buildings, net zero carbon buildings, carbon negative buildings, and absolute zero energy buildings. And I don't want to get tied up in all that kind of terminologies, but they're basically stages on a journey to which buildings move from being, just supplied with energy to meet loads that aren't particularly controlled, to being net carbon sinks. And that is possible in certain climatic conditions in certain types of buildings. Not, I should stress, for individual buildings in all climates. So there's a kind of journey. So we look maybe at just a little bit more detail at maybe the first stage of that journey, and the net zero energy building. And this simply is a building which has reduced its energy load, but has solar thermal, PV. It may have a heat pump, for example, that can be part of a district heat network. So when it is producing energy from the heat pump, but it's not being used in the building, it can go into that network. Or indeed, if it's a historic building, it may be actually drawing heat from a district heating network, which might have solar thermal, geothermal, heat pumps, etc., all linked to a network. So at certain times, it requires energy. At other times, it will be sending out energy to the grid. The illustrations on this slide are terrific for me. These are new net zero energy buildings. Is that achieving a low energy building is architecturally neutral. It doesn't imply any kind of architectural style or any architectural conceit that needs to be adopted. And all these buildings, quite different, are all net zero energy buildings, from very large scale domestic buildings using atria as glazed spaces to pre ventilation air, to buildings that are doing a large amount of thing around direct gain, storing solar heat from day to night, assuming primarily even occupancy in a domestic setting, through to very, very traditional forms. So a whole range of different architectural forms emerge. However, this kind of conceptualization for a consumer is not very helpful. A net or near zero energy building is actually meaningless to a homeowner because, as Nevin said earlier on, primary energy for electricity is time and location dependent due to the mix of generators and can rapidly change depending on how much gas is on that is used to generate electricity, how much renewables, etc. So your primary energy density is actually changing, in a 5-minute interval almost, depending on the kind of market structure, and is a primary driver of whether a building is net zero energy. So, and also it allows things like installation of PV and the counter of the export PV to offset imported fossil fuels as somehow a decarbonisation strategy, and not actually deal with the intrinsic loads within the building itself. So one needs care in terms of applying these kind of metrics. And my view is that it is the actual energy cost in the building itself, it is the building fabric, it is the efficient use of the energy within the building that needs to be measured and need to be the objective of energy saving measures. Otherwise, you can have perverse incentives to simply have PV on the roof, for example, which does nothing for the actual energy use in the building, or indeed simply encourage decarbonisation of the grid and have a lot of stranded assets which are producing electricity for winter heat peak loads, which are not necessarily the rest of the year, which have a net effect of increasing the overall cost of electricity to all consumers as a penalty for the few that don't decarbonise their buildings. So there's a complex set of interactions there. This also, by the way, applies to new buildings primarily, and new buildings are relatively easy to decarbonise. You set a regulatory framework that requires a certain, below a certain energy use per square metre. You set regulatory frameworks that require a certain amount of renewable energy to be installed, may even require heat pumps, would certainly require that you don't install a gas boiler, etc. And that all achieves a lot within new buildings. However, the rate of new buildings is always small. Buildings within the past 2 or 3 years are rarely more than 2 or 3% of our building stock, and in a recession could be even less. So new houses are a minority. And that leads you to this. And essentially this is a snapshot of Europe based on energy ratings. I'm going to talk about why this is not necessarily as good as it looks or as informative as it looks a little later on. But essentially the red here are the buildings that need refurbishment. And the little bit of the green at the bottom is essentially representative of the new building stock in these particular countries. So the real challenge with decarbonisation is not new buildings. That is met by regulation, is met by building standards, is met by a whole lot of measures. The real challenge is in the renovation of buildings and seeking to reduce the energy use in existing buildings. And there are multiple challenges in that respect. So what that involves is, and this particular example is of a social housing block, actually in Estonia, before and after energy refurbishment. And what it involves is improved insulation, How much depends on the particular country and the climatic context. Usually what's called a volumetric addition, which is that if you've got, as in this case, for example, balconies, they're enclosed and made part of the building, so that there are other gains as part of the process to the occupants. Draft proofing, reducing ventilation rates, very low heat loss windows, triple glazing, etc., vacuum glazing, things like that come into the play there. Renewable energy generation, so there'll be PV on the roof, etc. There might even be, as I say, excess energy produced from a heat pump, which is essentially stored for energy from summer to winter. That would be going to other occupants within the building. So a whole range of measures. Okay, but it isn't not as simple as it might appear. So, for example, if you look at the other picture I've got, which is a thermograph of a row of buildings, you might have several buildings that are refurbished, but one that is not. And this is because occupancy, ownership standards, tenancy, etc., comes into play here. So, for example, if you have a landlord, the benefit of energy refurbishment accrues to the tenant, not to the landlord. So a social landlord that has many properties and has a social mission might refurbish all their properties. A private landlord may not, because it would not necessarily make economic sense to them unless there were the granted incentives to do so. Also, if you're an individual homeowner owning identical homes, you can be in a different situation in terms of the mortgage that might be on that property and thus the cost of housing, so that if you still have a mortgage on that property, additional costs on the building may not be achievable, affordable. If you don't, they are. And also other issues to do with the economic position of the occupants come into play. So it's not simply a matter of a causal, we have low energy use, therefore we refurbish. There are a whole range of ownership, economic, social factors that also come into play. And because of all those factors, it needs quite complex and subtle interventions to alter perceptions and alter how those particular individuals are going to be able to refurbish the buildings based on their particular circumstance. And it's very difficult to devise regulations that either aren't too generous to people who don't need incentives, or can be gamed by people, or misdirected importantly. But it's important that actually it is done. This, and I should explain, this is a calculation we did for the European Cannabis Science Advisory Council report, and huge range of very hairy assumptions behind this. So, but the broad message, I think, is clear. What this is if you looked at the effect when you work it through to global temperature rises of refurbishing buildings in Europe, and it assumes everything else remains constant, which of course it won't. But nevertheless, just as an illustrative exercise, it's quite interesting. And if you had just business as usual, if you did not refurbish buildings, you did the decarbonisation of the supply system that's planned, etc., you'll completely overshoot any kind of target in terms of reducing global temperature rises. Even with the current EU renovation wave, which is lagging behind in progress of where it actually should be, and still remain a whole range of challenges, as I mentioned earlier on, by the economic capacity of various countries to support the kind of interventions needed to enable homeowners to refurbish their houses. Even that is barely going to be able to achieve a 2 degrees Celsius temperature rise. And certainly the idea of a 1.5 degrees global temperature rise has gone out the window. So if you relate these things to end targets in terms of global warming, and you've got a whole lot of intermediate stages of the actual emissions, how they're affected climate, etc. Certainly the renovation, where the renovation of existing buildings is critically important. Okay, but I mentioned that I discussed some of the key challenges that there are in buildings. And one starts off with actually what do we know about energy use in buildings? And what might to some of you be surprising is that no country anywhere actually measures how much energy is used in buildings. Sounds surprising. So there's a whole lot of policy interventions to be made, and there's actually no evidence base whatsoever as to what the energy use in buildings actually is. What they actually do is they use the energy ratings of buildings. And what an energy rating is a calculation based on a standard set of assumptions to do with climate, occupancy, etc., that are then essentially modified to the particular physical characteristics of the building at a particular point in time. What is its heating system, how well insulated it is, what's its glazing system, etc., floor area, those sort of things, to produce a rating. And the original intention of ratings was as a means of offering government grants for refurbishment of buildings. Okay? So you're comparing, if you like with like, that this building by this method gets a better rating than this other building. Okay? And that's okay. As a comparative rating, it's fine. But then what's happened is the numbers associated with those ratings, and bear in mind the building is only rated when it's applying for a grant or when it's sold or rented, and when it's constructed. So not all buildings are rated, okay? And not all buildings are equally rated by type. So you find that there be rather more social housing that's rated than, for example, large detached houses. You'll find different rates of rating depend over time, depending on what grants were available, okay? So you might have 5% of the buildings in a particular category rated, and then that's extrapolated for the number of buildings in that category. So 5% of the semi-detached houses in the country, say, will be rated. That rating will be extrapolated to all the semi-detached houses in the country, and that is what the government will use to say that's the energy consumed by those buildings. That is all flawed, because the theory behind that is that whilst the individual rating may not apply to the particular building, because it's all comparative, all right, summed up, some will be higher, some will be lower, etc., and it'll all iron out. That has proved to be a false assumption. So as you see from this graph here, these are graphs of actual energy consumption against theoretical energy consumption for buildings where actually measurements have taken place. And essentially what happens is that the energy ratings of new buildings are too generous, and that's because the occupants of the buildings take some of those gains in terms of improved insulation, etc., in terms of higher comfort temperatures. They sit in their T-shirts and shorts more into the winter. Okay, and consume more energy. So you get what's called a rebound effect. So new buildings are seen more efficient by a rating system than they actually are. Older buildings, even more interesting, are not as energy inefficient as you'd think they would be. And the reason for that is an assumption in these calculation methods that buildings remain, in terms of the building fabric, at the state they're in at the time where they're constructed, according to the building regulations at that time. The flaws in that argument are twofold. One is that the building regulations at that time represent a lower standard, and many builders will build above that standard, inadvertently or intentionally. So even at the point of construction, most buildings are not meeting the minimum standard. But also through their lives, householders improve insulation, they add parts of the building, garages, conservatories, additions, which provide a thermal buffer to the building and are also better insulated. They might draft-proof the buildings, etc. So actual energy consumption in older buildings is not as high as people imagine. That has important implications in terms of how you calculate what is the appropriate refurbishment intervention. If you don't know your starting position, how do you get to your end position? So lots of issues to do with the rating of building. Now, there's also, I should say, an awful lot of work on trying to improve rating systems so that they don't have this conflict between what this idea of being a rating system and actually being used then for national policy in terms of buildings. Another issue, and again it's been touched on already, is that buildings are part of a system, and looking at buildings in isolation can achieve a suboptimal system. So you've got buildings that might have, for example, a PV prosumer, battery, there might in the future also be fuel cells in buildings, there'll be heat storage, etc. But there's a whole lot of other parts of the building, parts of the system, where there'll also be storage with varying timelines and varying technologies. For example, a PV operator might actually have batteries at the PV field, at the PV generation point, so that they can achieve a better capacity factor to the grid by supplying stored electricity from their own batteries, for example. A grid may choose to have hydrogen. One of the potential applications of green hydrogen is, for example, in generation in the depths of winter and effectively storage for that. The other one, by the way, is decarbonisation of industry. But they may have hydrogen storage at the grid level as well. You might also have pumped storage. We do in Ireland, do in Wales, for example. So you've got pumped hydro. So there's a whole range of storage options within the grid. And it leads to very critical questions about where you store. Is it at the demand side? Is it somewhere along that supply chain? What you store, is it electricity, is it heat, is it potential energy in hydropower? And and why you're storing it, for what purpose. In other words, is it to discharge at the end of the day? Is it summer to winter? Is it to regulate the grid, etc.? And all those choices of storage are become very important in terms of the interventions that are made at the building's end as opposed to different parts of the system. In other words, looking at the whole thing as a system becomes important. So, for example, I was just mentioning before I came up that the intervention of district heating in Ireland, which would not traditionally have district heating systems, is currently has two sources. One, which is the heat generated by data centers, of which we host a large number, and they use a lot of heat, okay, and they can be used in those localities. But in other localities, it's geothermal, and geothermal going into district heating because we have lots of long extinct volcanoes which have left a residual heat signature in the ground. So looking at systems aspects, and those systems aspects then saying, well, the dwellings are also linked perhaps with educational facilities, linked with hospital facilities, etc. in those networks, then gives the kind of loads and balanced loads over time that makes those kind of systems viable. So looking at things from a system perspective is particularly important. Let's say a bit of a random walk here, but one other issue, and this actually came up very much in the COVID-19 pandemic, is indoor air quality. And this goes back to a point I made right at the beginning, in that the primary function of a building is not to save energy. The primary function of a building is to be in habitation, is to be a lecture theatre, is to be an operating theatre, is to be whatever it is, and needs to achieve that role perfectly. And one of the critical roles, particularly if you look at domestic buildings, is to provide a healthy, comfortable internal environment with the amenities that people wish. Healthy and comfortable. And part of a drive toward low energy buildings was to reduce air change rates, reduce the ventilation rate in buildings, because you've essentially got a fabric heat loss and you've got a heat loss of that warm air being expelled from the building. That is not a good strategy, because what it means is that you've then got a persistence of the air, the quality of the air in terms of the pollutants in the environment, again, depending on the cooking culture, etc. But as particularly came true in the pandemic, also the ability to flush the air, flush airborne pathogens out of the building is reduced if you've got very low air change rates. So strategies in the future are going to be some combinations of the preheating of ventilation air, either in non-domestic buildings through, for example, atria as a source of a preheated ventilation air, or through double screen windows, etc., combined or separately having mechanical ventilation heat recovery from the building and having that controlled in such a way that it's controlled by the air quality within the building. So air quality accepting a higher air change rate, but then having an intrinsic energy conservation strategy around that, rather than simply reducing the air change rate itself, becomes important. So some of the sort of measures that we're taking in the past in terms of very low air change rates are very unwise in terms of various aspects of human health. Most of them discussed on that figure. A similar thing happened in terms of how buildings had windows. You see these trends where people are saying heavily insulated buildings, very, very small windows with lots of low energy lights, so that's a strategy. It's flawed for a whole range of reasons. Over the last 15, 20 years, there have been a lot of discoveries about how the human eye interacts with the human circadian system, our body clock. And there was a discovery of a new type of cell within the eye, intrinsically photoreceptive ganglion cells, which control the human body clock. And it responds to green, blue wavelengths that are particularly prevalent in the solar spectrum, and it's why we like to be in environments where there's lots of green around us, for example. And artificial lighting, traditional artificial lighting, does not have those wavelengths in the spectrum. So from a point of view of providing circadian health, etc., artificial lighting, you might have as well have been in a dark room. So having too much artificial lighting is bad for your health in terms of that process with the building. Also, for the eye development in children, unless they get regular exposure to sunlight, you get short sightedness, myopia. And so there are now so-called pandemics of myopia in places like Singapore, Taiwan, etc., where children move from indoor environments through underground passageways to indoor environments that are in shopping centres, etc., because of the climate, because of the hot weather, essentially, and never actually see the sun. They see a lot of artificial lighting. So a whole range of sort of adverse consequences of no daylight. So much more of an interest in terms of much more daylight coming into buildings, better for human health, better for human development, etc., has an influence on the form of buildings, which is going to be important in the future, but also has an impact on energy. And that is that if you look at a low energy light bulb, it consumes a fifth of the energy of an incandescent light bulb. Okay, about a fifth. Okay, if you saw a typical domestic situation, maybe 20 years ago, you would have seen a room would have been lit with one incandescent light bulb. Okay, the same room today will typically have 10 recessed LED light bulbs. So your LED light bulb uses less energy, about a fifth, but you've got 10 of them, so your energy is actually doubled. So lighting energy use is actually going up. So increasing the use of daylight in the building to displace electric lighting is becoming proportionally important, and it's becoming proportionally important because all the other energy uses are going down. So designing for daylight, as you see in the diagram here, is also becoming important. So trends around reduced air exchange rate, very small windows have kind of bottomed out, and you're seeing trends going the other way, which imply highly insulated windows, triple glazing, vacuum glazing, etc., shallow plan buildings, but also, because again, avoiding inadvertent consequences, avoiding overheating, avoiding glare, working out glare much more carefully, and discomfort glare, etc. So a whole range of trends within buildings. The other very big and very well-established trends is that if you looked at the regulatory environment around building regulations, it has been primarily concerned with operational energy use. In other words, what energy is actually consumed in the operation of the building. But as you reduce the operational energy use, the actual energy in the construction, maintenance, etc. of the building becomes more and more significant, the so-called embodied energy. And it's embodied in materials, but also embodied in the transport of those materials to the building, etc. And you see these kind of things of looking at energy over the life cycle, and you see various things where you see these kind of ideas of a pyramid of materials, depending on how sustainable they are, with steel and concrete at the bottom, essentially, and wood at the top. Now, that's very simplistic because you can recycle steel, and you can increasingly see various versions of concrete that have low energy content. But nevertheless, a hierarchy there. But there is always an embodied energy associated with materials you put in buildings. This also applies to building refurbishment. So when you're refurbishing buildings, you're seeking to reduce the energy use, but in the very act of doing it, you're increasing the immediate energy embodied in that building. So there is a payback period over which your operation emissions need to be recovered. So this graph here, you see this line, that period of increase, you've actually got increased global warming, increased emissions because of the renovation. Okay, but the operational use is going down and eventually pays that back. And then you start saving energy overall. But if your goal is to reduce CO2 emissions in the short term, okay, you can't have that energy payback period for the embodied energy against the operational energy too long. It needs to be as short as possible. So again, look at the embodied energy material becomes very, very important. It also has an implication because the targets that government set for energy refurbishment have a cost optimum. So they're ending up moving from a rating E maybe to a rating B of some kind. But if you brought embodied energy into those calculations, and you also brought into those things calculations around what the actual energy use of an older building was, which I say is not often as much as you might think, the optimum calculations also change. And in fact, the net effect of all that lot is that the targets for refurbishing buildings should actually be very substantially increased. So, some big issues that come out of that. I mentioned earlier on one of the big issues are the economic, social factors in this. And it's not my particular area of expertise, but I think it's important that it's included in the discussion because a lot of the barriers to energy efficient in building are not technical. They are market structure issues, they're social issues, they're financial issues of various kinds. So you see a whole range of new measures that are looking at affordable financing schemes that persuade building owners, whether they're landlords or literally building owners, occupant owners, to refurbish their buildings, and a wide variety of these things. My own view is all of them need very strong market regulation, which is consumer-centered, and indeed even the people who do refurbishments, you increasingly look at one-stop refurbishment operations. Also, they need very, very strong market regulation. Otherwise, I think homeowners are going to be spending more money than they should do. And one of the key issues, literally the elephant in the room on this, is fuel poverty. Fuel poverty is where the occupant of building spends more than 10% of their disposable income on energy. And it has two factors. There's the energy cost in there, and there's the income of the home occupant. Energy costs have increased, but also because of recessionary pressures, incomes have decreased. So the number of people in fuel poverty has actually substantially increased and varies widely throughout Europe particularly. And there need to be interventions that basically do the job for those occupants and refurbish the buildings without, in my view, any cost accruing at all to the occupants. And schemes that do that would need, again, to be very carefully regulated, carefully policed, to make sure that there is not inappropriate profit-taking, etc. But it is a critical thing to do. Okay, to bring this to a conclusion, there are, in energy and decarbonisation of buildings, there are multiple different factors and actors. Architectural things, technical aspects, issues to do with climate that I've not really touched on this morning, a whole lot of economic factors, even planning factors, where buildings are located, where they're co-located, their access to solar radiation, for example, the sustainability of the transport network that serves them, all those kind of issues. So that energy buildings has a whole range of factors that influence it. There are multiple benefits that accrue in terms of reducing CO2 emissions, in terms of quality of life for the occupants of buildings. Some of those are for the public good, some of those are private good, and there's a regulatory issue there as well. So things accrue differently to different stakeholders. I mentioned already the influence of what accrues maybe to a tenant as opposed to a landlord if you refurbish the building. But the holistic picture needs to be taken into account, and regulation needs to make sure that all those multiple benefits are instant in terms of each instance of policy decisions that can be carried through to maximum benefit overall. And indeed, it needs a political philosophy that assumes that there are both public and private goods, and that's a politically contentious position. Okay, to summarize. There's no silver bullet. There's no one thing that decarbonises buildings. Certainly needs to be a revised legislative framework, and we saw inclusion of, for example, domestic gas in the ETS would do some of that to get to near zero greenhouse gas emission buildings. There is the need to completely phase out fossil fuels and supply renewable energy, decarbonised fuels into buildings. And again, that is subject, it's obviously to do, but it's subject to pressure for incumbents. The very long lead times on replacing things that are being installed now, and indeed with certain kinds of installations where you might have a gas backup in a heat pump, for example, is that gas backup really still a gas boiler? Those things like that. Reduce the energy use of buildings, obviously, so lots of insulation, ventilation, heat recovery, the highly insulated windows, draft proofing, etc. Looking to reduce the embodied CO2 emissions in building materials, components and systems, so decarbonisation of the steel sector, of the cement industry is critically important, and that will require replacement of feedstock, so more renewable electricity in steel production, probably hydrogen in cement production, and much greater efforts on waste heat recovery in the cement sector. There's huge opportunities there which have not been realised. As I've said, promoting investments, and then using all kinds of grants, incentives, so that we are tripling, doubling the current rate of building renovations. Thank you very, very much for listening. Happy to answer questions.
Thank you, Brian, for finishing very quickly in time. Henrik, we need a microphone. A microphone is there. Okay.
Thank you very much. And thank you very much for an excellent presentation where you really highlighted the many challenges of decarbonizing the buildings. I have been involved a lot in the district heating and district cooling technologies. Also been involved in making Heat Roadmap Europe, the many studies for the past 10 years. And with that background, I was a little bit disappointed on your slides in the beginning, because you were always talking about supplying the buildings with electricity and fuel, and you didn't mention heat and cooling from district heating and district cooling. Then in the middle of your presentation, I was very happy because I saw the word district heating for the first time. Then I was a little bit disappointed in the conclusion because you didn't mention it there. So what I'm trying to say here is there is an emerging, for example, district cooling. There is an increasing number of district cooling in Europe now. And they have a very interesting role to play. When we are insulating the building so much, we also are increasing. Also in Scandinavian countries such as Denmark, Sweden, Finland, we have district cooling systems. They can decrease and make more efficient the electricity for cooling by a factor 10, sometimes even more. So my question is, why have you left out district heating and district cooling, and what is your view on those, for me, important technologies? Thank you.
Thank you. I first of all agree, and in a short presentation one can't deal with everything comprehensively. And as you saw, particularly in the connection between buildings and other sectors, district heating is critically important. It also has, I think, a critically important role in historic buildings, where the kind of interventions at an individual building level for heat pumps in many systems may be very difficult. So it has a very important role. My view, maybe slightly contrary to yours, would be that there are circumstances where you've got a district that you can heat. And a lot of those have been taken in Europe. Often the district heating may be coal-fired, but it exists, okay? In other parts of Europe, you don't have something that could be recognized as a district. I live in Ireland. Ireland, aside from 2 large cities, is primarily rural. And it would not be cost-effective to use district heating in that kind of context. So the amount of increase of district heating from where it is now may not be great, and that particularly in some jurisdictions. So I think it's a matter of horses for courses, and if the district heating option in historic buildings, and even sharing heat networks in groups of new buildings, for example, and sharing the energy from a heat pump that's generated to get capacity factors would be good. But I think in terms of interventions, even with new district heating networks, you still want to reduce the actual energy consumption to make the district heating network viable in itself. So there's an optimization between the two that needs to take place. And in my opinion, it's not one or the other. It's an interaction of these things that you're both looking at the actual demand and you look at the supply. But certainly I would totally agree that it's the production of new energy to the building, either electricity or heat, but also reduce the use of energy in the building itself that becomes important. I'd also, by the way, believe that actually energy storage in buildings also needs a lot more attention as well. So there's a variety of things there, but I think it's geographic context and market maturity issues come into play as well.
More questions? Birol?
Thank you. This is Birol Kılkış, and thank you very much for your presentation, and also thank you, Professor Lund, for your comments. So on the side of Dr. Lund, I would suggest microgrids, micro-district energy systems, if we are speaking about rural areas. This will also help to level off the peak loads by prosumer buildings, and therefore there are several advantages. And in the case of district heating, the only caution that I would like to make is the pumping exergy. If you go to a very large district, the pumping exergy demand might exceed the exergy of the heat that you distribute. And this, in this case, will be responsible for nearly avoidable carbon dioxide emissions. So the solution might be of course, after optimizations, micro and mini district heating, if the pumping exergy is crucial. Thank you very much.
Yeah, I don't disagree. I think, though, as I said at the beginning of the lecture, in terms of looking at energy in buildings, one needs to start with the actual loads of the building. What is the distribution over time of the heating, cooling, lighting, cooking, hot water loads that are there, and then devise solutions that meet those, okay? Rather than starting off with a technical solution and saying, I believe in district heating, or I believe in solar thermal or PV or whatever, and that's the technology. The technology will come out of the application, and there will be applications where a micro district heating system would be appropriate to the loads, to the co-location of the buildings, to the climate, etc. There'll be others where other strategies will be more viable. And I think, I don't disagree, but I think it needs to come out of an analysis of the building rather than any technocratic solution that's imposed upon the building.
Thank you. Ingo?
Yeah, thank you very much for your presentation. When you less see the district heating system as a solution, but more the renewable electricity, and you do not only look on a single building, but on the building stock, did you also take into consideration in your research the effects on the grid infrastructure when a large majority will go for electric heat pumps? And there is a need then for heat storages or other storages? And in case yes, in which time frame do we need those storages?
Yeah. My own view is that one of the reasons you need to reduce energy use in buildings to start with is to reduce the load that's met. So you're not meeting with the current electricity infrastructure the current load. You're meeting with a future decarbonised energy infrastructure, a lower load within buildings, but also new loads in the decarbonisation of industry and new loads in electric vehicles, for example. So there are other pressures on the grid, particularly from electric vehicles in timing, that are going to be far greater than... So the first step is to reduce the energy use in buildings, okay? Then seeing how the energy use is best met, and it could be, for example, with the electricity to a heat pump. It could be through district heating. As I've said already, there are particular building types, historic buildings being one, by the way, which that's applicable. Or there may even be particular heat sources, waste heat from data centers, geothermal, etc., which make district heating particularly attractive in a particular location. So, but certainly the key thing is to actually reduce the requirement on the grid from buildings in the first place. Okay, there will be other requirements that are going to increase and indeed don't even currently exist, which will also influence that in the future.
Thank you. We have one question there. I'm not seeing the person, so... Oh, okay, there was one here. I see the lady there. Please introduce yourself.
Thank you very much. Katharina Gab-Schmeling from Germany, from the ITES Research Institute. Thank you very much for your talk, which kind of summarized all the challenges that we came across in Germany for the heating transition in the building sector. I have a totally different question, because you now discussed district heating so far. What about, because we discussed this in our institute and in Germany as well, so I'm interested in your opinion. What's your take on carbon prices to use to finance funding for low-income houses to have their owners do the renovation? Thank you.
So what sort of prices? Sorry, I didn't quite catch that. Having what prices?
If you have carbon prices and you use them to finance the renovation for low-income homeowners.
I don't understand. You have to explain. Oh, carbon tax.
Okay,
oh,
sorry.
yeah, okay. Yeah, taxes. Yeah, okay. To be honest, that's essentially what most states do. The actual, one way or another, they are recycling levies to offer subsidies to low-income houses. So that essentially is what a large number of states do. One needs to be careful in the detailed construction of how that pricing is done. if I give an example of that, if you look, for example, in many jurisdictions, an electricity bill will have two components. It'll have a variable component depending on how much electricity you use, and it'll have a fixed component, which is a legacy of when electricity systems were socialist and everyone contributed to the maintenance of the grid. So there's a fixed component, all right? A lot of people say reduce that fixed component and that would reduce fuel poverty, etc. Unfortunately, the amount of energy people use doesn't correlate with their income, all right? So that if you did that, in fact, the prices would go up to poorer people, etc. So one does need, when we introduce costs, new taxes, new interventions, that they don't, whilst giving money that enables certain measures to be done, they don't also, prior to that, penalise the very people who the measures will actually then affect. So there's a very careful construction of how the revenue stream isn't actually taxing the people who are going to benefit, it's actually taxing other people and resulting in a net transfer. So that just is something you need to be very cautious about. It can be done. It's not. I'm going to say it's not difficult. It is difficult, but it's not impossible. But you do need to be very careful. There are already lots of distortions in energy markets, particularly in consumers. In fact, electricity market is a good example. You talk about electricity market. I believe it's a market on the wholesale side, but in many jurisdictions, it's not really a market at the retail side. The ability of people to behave as consumers to behave as market actors is very limited, and that applies with any intervention on fuel poverty.
Thank you. Peter?
Peter Varbanov from Bern University of Technology. I have this question. I fully agree first with the hierarchy. First should be energy saving, especially considering the shares of how much energy is used and how much energy is wasted in the economy and especially in buildings. So the question within this context is how do you see the role of integration of energy flows, thermal flows especially, inside the buildings, between the buildings, and maybe some storage, short-term, long-term. What do you think?
Yeah, first of all, storage is going to be critical. Storage in the building at a variety of levels, storage within the system, electricity systems, the district heating system, etc., are going to be critical in terms of matching energy inputs to energy requirements. And systems do need to be revised from a system perspective, because your prosumer, if you're producing photovoltaic electricity, or indeed you're producing heat from a heat pump that you haven't got use of yourself, you need to have both the physical systems and the market models that enable others to then take those energy from you in real time, okay? And most of us are not going to be trading electricity from home sitting here, so it needs apps, it needs providers, it needs facilitators that enable all those things to happen in a fair way, in a transparent way, and in a regulated way. But yeah, I think system integration is going to be key to the future, both in terms of heat systems and electricity systems, and particularly when you look at examples where you might have distributed interseasonal heat stores, maybe thermochemical, etc., which would serve a number of buildings. That will become very, very important.
Thank you.
Thank you. Well, I would like to ask from my side, there is a lot of discussion on social networks. Whenever I write we should go to electrification of heating, the response is we first have to retrofit the buildings. So it's a kind of delay tactic. Let's do it in 20 years' time, because it takes a long time to retrofit all the buildings. I am living in an 1850 building, which is probably G-class, and was not able to retrofit it because other neighbors don't agree with that. And I wanted to move away from gas. And they didn't want to bring me district heating, so I put a heat pump. And it works very well, no problem. No insulation whatsoever, and it's perfectly warm inside. So why, what do you think about that issue? I agree that we should retrofit, but it's not a precondition to decarbonize the heating, in my opinion.
No, and you are correct. It goes back to the point I made earlier on. You start with an analysis of the building. What is possible, what is desirable, and for example, a historic building, older buildings, there are limits to how you can change the fabric, you change the glazing, etc. So in those circumstances, a focus on decarbonising the energy going into the building and the systems that harness that energy in the building, heat pump in your instance, would be important. However, there are many, many other buildings which exist of higher, whole groups of buildings that are very, very similar, where a group refurbishment could be done within a month, 2 months, often with interventions that are exterior to the building, so you don't even need to decant the people out of the building to do it, and would substantially reduce the energy use of those buildings, which could then be part of a district heat network or part of an electricity network. So it starts off with an analysis of the building in all its respects. What is its function? What are the constraints? What are the opportunities? And then flows from there. Again, not following a dogmatic position that you have to refurbish everything, okay? Or a dogmatic position, which is an equally dogmatic position, that the solution is simply to decarbonise the grid. It's a case-by-case kind of analysis that needs to be carefully done.
We are now already moving into lunchtime, but we have 3 short questions, please.
Yeah, well, it's not a question, but a remark. I'm Ivo Potov from TU Delft. I fully agree with your own personal experience with N equals 1, but luckily we did a large-scale measurement campaign in the Netherlands in 200 individual dwellings that confirmed that 60% of those dwellings is already LT ready, you can say, so ready for low temperature heating without any modification to the heating installation or the building envelope. And that gives a lot more flexibility to decarbonize the existing building stock. And the journal paper that we drafted on this topic has just been accepted for publication in Energy last Friday, so it's currently in publication. So I can confirm your personal experience with a large-scale experiment.
Yeah,
Thank you.
But actually just on that, and congratulations on the paper, but the point I was making earlier on is that because there has not been wide-scale measurement of the energy use in existing buildings, there are lots of assumptions that older buildings are energy inefficient, that for lots of reasons, and as I said earlier on, to do with how the calculation is done and to do with what homeowners actually done to their buildings, is not always true. And so you need to start off with a real evaluation of the particular building.
Reinhard?
Also a remark. Neven, do not take it personally, but I think you do not heat with electricity from renewables. Because in winter time, when we need a heating system, we generate the marginal kilowatt hour, I don't know, from natural gas or even from coal. And maybe in 10 or 20 years, we managed to have the 100% renewable system, and then it could be the case that you heat renewable, but I think it's not the case today.
Okay, that's a question to me, I would say. Well, I disagree with the marginal approach, because if we look at the marginal approach, we're going to wait for a very long time until we completely remove gas from the power sector. The average carbon intensity of electricity is extremely low now in Europe. If you take into account COP, even heating sometimes on gas is not that bad with COP3. And if you are doing it with district heating and have heat pumps which have COP6, you're excellent, even with gas. So I think we should do these things parallelly. I don't know if you want to...
No, I would...
Okay, we have one more question there, and then I'm closing it.
Last comment here, Robert Advice from VTT Finland. I support your comment about the heat pumps, and I would like to stress that you can also install hybrid heat pumps that work most of the time in heat pump mode when you have cheap electricity, renewable energy, and in the peak times in the winter you can use a little bit of gas to boost it, and it works well. The main issue, as I see, is commercial and tariff if you have very high electric power rates and very cheap gas, as we had in many Central European countries, not Finland, but Central European countries, and no heat pumps will be installed because of economical reasons, not technical reasons. So this, in my opinion, is a very economical and economical control question.
That's why we should stop subsidizing gas, and then you solve the problem. You want to comment?
Yeah, no, I mean, I think fossil fuels need to include their externalities in the price. That's a more polite way of saying what Nevin's just said. But also, market structures do need to reflect the real costs of energy production and real profit margins. So, for example, where renewable energy was tied to the price of gas because it was the lowest price fuel, renewable energy costs went up when gas prices went up. That's not unexpected, and you need, when you're developing market models, to actually do the risk analysis, do the what-if scenarios, so that your models are robust and don't allow profiteering, even by renewable energy operators. You know, there's a simple view of saints and sinners in these things, of renewable energy being saints and fossil fuels being sinners. That's not true. And market signals and market constructions can give very strong perturbations of markets that work against consumers and work against energy efficiency.
Thank you. Thank you, Brian. With this, we close this session, and now it's the most important session of today, the lunch. Let's see you back in parallel rooms in 1 hour.